Okay, so we'll start renal physiology today, and along with this we are going to do fluid compartments and a little bit about acid-base balance. Okay, and how we already did a little bit when we were doing the respiratory system. You remember how we talked of hyperventilation when there was too much CO2 in the body and hypoventilation when there was less, so we'll kind of revisit that. So let's first look at urinary physiology, which is how urine is formed. So if you remember, we said that the kidneys filter blood and form urine, and then the ureters, urinary bladder, and the urethra were just transport organs, right? So when they filter blood through the glomerulus, it passes through a filtration membrane. And it's really important for you all to know what the filtration membrane was. If you remember, it was the glomerular capillary endothelium. And then there was that fused basement membrane of the capillary endothelium and that of the visceral layer, or also known as the basal lamina. And then it was the visceral layer of the Bowman's capsule, and the special cells which were present in this visceral layer of Bowman's capsule, they were like foot processes, so they were known as podocytes. If you remember, we had that, okay? So either you say visceral layer or you call them podocytes. So that forms the filtration membrane. So then that gets filtered, so the blood gets filtered, and then since anything which is large or heavy, the molecular weight is big, that won't get filtered, but everything else gets filtered. So you even have important substances which are filtered, like glucose and amino acids, all that you absorbed from the gastrointestinal tract, much of it gets filtered. Now you don't want that all of that to pass out through in the urine. So you've got to reabsorb some of those important substances. And the reason we call it reabsorption is because absorption occurred in the intestines. Okay, remember you absorbed nutrients in the intestine. Those nutrients now get filtered through the blood in the kidney, and you're actually reclaiming them back. You're kind of reabsorbing them back. So in the kidneys, we use the word reabsorption and not absorption. Okay, so that's why we use the word reabsorption. So from all that is filtered, what is filtered is called the filtrate. You reabsorb some of the important substances. And then some substances may not get filtered properly or they may be reabsorbed just because the concentration is more in the tubule. So you need to get them out. And these are waste substances which your body doesn't need. So what you do is you throw it back into the lumen of the tubule so that it can go out in the urine. And that throwing back is known as secretion. So we will look at these three processes, that of filtration, that of reabsorption, and that of secretion. Okay, so these are the three that happen. The purpose, why do you form urine, is to regulate the volume and composition of blood. And you all, we've been talking about the endocrine system, and we saw when fluid volume was low, how ADH was secreted or even aldosterone was secreted. Then when we did the respiratory system, we were talking about pH. Remember, if the pH of the blood is high, then you have hypoventilation. If the pH is low, you'll have hyperventilation. So, you want to keep the blood pH constant at all times. You also want to make sure, like if you have too much of sodium, then you throw out the sodium. If you have too little sodium, then aldosterone reabsorbs it. So you can see the function is to regulate the volume and the concentration of blood. And this tells you how well all these processes have to work, because you filter about 180 liters of blood every day, but we only pass 1.5 liters as urine, and sometimes even less, because if you are dehydrated or something, your body the urine passed out would be even less, which means the reabsorption has to be really good, because you cannot filter and throw out all of the blood that you have filtered. You cannot sort of throw it out as urine, otherwise you would you'll have a low blood volume. So you can see how well the kidneys have to be functioning. So here are some terms that we use. The first one is filtrate. So that's what happens in the glomerulus. So when blood is filtered, what passes into the Bowman's space is what is known as filtrate. And as I just mentioned, large substances like large cells or heavy substances like big molecules, they do not pass into the filtrate, because the filtration membrane has very small pores. So only small molecules can pass through. So filtrate is your plasma minus cells. So you never see red normally. You never see red blood cells. You never see white blood cells or platelets in the urine. You also don't see large molecules like protein, albumin. You don't see that in the urine. Women who are pregnant, you often do a test on them to see if they have protein in the urine, because then it kind of tells us that maybe there's a problem with the kidney, okay? So if there is a problem with the filtration membrane, the pores are damaged, then you will end up finding cells and proteins in the urine, and so the body will lose that. What is urine? Urine is then actually formed from the filtrate. So as this filtrate passes into the Bowman's capsule and then it travels all through this whole nephron, that's when that reabsorption takes place, and then you secrete some of the unwanted substances. So finally what comes out into the collecting duct and into the minor calyx, that is known as urine. So urine is really formed from the filtrate. It contains all your unwanted substances. You never throw anything that is wanted unless there is a problem. For example, the filtration membrane is damaged. So it mainly contains metabolic wastes. The amount is much less than the filtrate, right? You filter quite a lot of blood, like 180 liters as it was said. But the amount, what passes out as urine is much less. And the function is to regulate the volume and composition of blood. So let's see the three main processes which take part in urine formation. So we just saw that in the first slide. So there was filtration, which occurs at the glomerulus. So here you remember when we did anatomy, this was the cortical radiator, also known as the interlobular artery. It sent out the afferent arteriole, which was of a larger diameter, that broke up into a capillary plexus, and then from that we got the efferent arteriole, which was a smaller diameter, so that was a pressure established here. And so as blood flows through, because here is the filtration membrane, there are little pores, so this is where filtration occurs. So you can see it occurs into this capsular space or glomerular space. So filtration is occurring in the glomerulus. This filtrate passes down into the tubule. As it is passing down, like I said, some important substances are reclaimed. So that is known as reabsorption. And even in the intestine, if you remember, where does absorption finally occur? So it passes through the wall of the intestine, the epithelium. Where does it finally go when you absorb nutrients? Yeah, but first, before it goes to the liver, where does it go? The bloodstream, right? Remember you had blood vessels in the lacteal, and blood vessels in the villus and the lacteal. The fat went into the lacteal, but other substances went into the blood vessels. So the blood is finally going to carry it, right, into the liver for processing. So absorption in the intestines occurred in blood vessels. Reabsorption also has to occur then in the blood vessels. You have to reclaim it and go into the blood vessels. So you should then understand that as the filtrate is passing down here, this is the renal tubule, and the first part after the Bowman's capsule is the PCT. Do you remember? Then it becomes a loop of Henle and distal convolution. Here they're just showing you the PCT. This is lined by cells, right? Remember, there were actually tall cells in the PCT like this. So I'm just drawing it this way. So when the filtrate passes into the proximal convoluted tubule, it will pass from the lumen into the cell through this interstitial connective tissue space, and it will go into the blood vessel. So that is from the tubule into the blood vessel. So can you see these arrows? This is 2. That's the process of reabsorption. And then finally there's the process of secretion, where some substances maybe they just didn't get filtered, but the body doesn't need them. And a good example is, for example, urea. The body doesn't need it. You need to get it out of the body. It's a waste product, okay? Or maybe there are certain drugs which kind of pass through and the body really needs to excrete those drugs. So now you need to it didn't filter through like this so that it could pass out. What happened was it went this way. So the kidney has a backup mechanism, and that's known as secretion. So what secretion does is, because remember those peritubular capillaries and the vasa recta, which was so close to the renal tubule, and I told you when we were doing anatomy, pay special attention to that. So in secretion, what happens is that those substances from the blood vessel, it is kind of reverse reabsorption. So from the blood vessel, those substances will pass out into the interstitial connective tissue space, from that into the tubule cell and into the lumen, and then get out in the urine. So secretion is from the blood vessel into the lumen of the tubule, okay? So in an opposite direction to that of reabsorption. And here it's showing you the filtration pathway. So remember, it was those podocytes of the visceral layer, the fused basement membrane, and the capillary endothelium. And in between them, you have these tiny spaces. So these spaces are really small. They're called filtration slits, and they only allow small molecules to pass through, which is why you don't have blood cells and big protein molecules in the urine normally. So let's look at some of these questions. So let's review this part. So what is the purpose of urine formation? Yes, the purpose is to regulate the volume and composition of blood. It does get rid of wastes, but look which is the best answer. By regulating the volume and composition of blood, it also takes care of waste. So always choose the best answer, okay? Its function is also to retain important substances. So this takes care of both. So this one is the correct answer. So let's look at the first step of urine formation, which is glomerular filtration. So this, as we said, occurs in the glomerulus and passes through the filtration membrane. And here you can see the filtration membrane. So this is the visceral layer, and this visceral layer has these cells which are known as podocytes. And then we have the capillary endothelium and the fused basement membrane. If you remember, the afferent arteriole was much larger in diameter compared to the efferent arteriole. So when this goes in and breaks into a capillary plexus, blood goes in rather fast but can't come out as fast because this is thinner. So what happens, it sets up a fluid pressure there, which is the hydrostatic pressure, okay? And in the capsule here, in this capsular space, there may be some filtrate which is present from the past that exerts what is known as an osmotic pressure. So hydrostatic pressure always tends to throw fluid out. Osmotic pressure always tends to draw fluid back in. And hydrostatic pressure is 55 millimeters, so that is more. So that's what throws the fluid, the blood, the filtrate. It passes through and gets into this capsular space. Then plasma proteins and cells which are really large, they cannot cross the filtration membrane normally, so they go back in the efferent arteriole. However, smaller substances and water, which always passes through fluid membranes very easily, so water, glucose, amino acids and waste, they cross through the membrane quite easily and get into this space. And the rate at which filtration occurs, this is known as glomerular filtration rate. And this is about 120 to 125 ml per minute. And the way this glomerular filtration can be modified is based on hydrostatic pressure. So imagine if you did something like you increase the diameter you caused vasodilation of the afferent arteriole even more. So you made it even more dilated, but didn't do much to the efferent arteriole. What do you think would happen to the filtration pressure in the glomerulus? Would it increase or would it decrease? So I'm saying that you have increased the diameter of the afferent arteriole only. So what happens to filtration? Does it increase or decrease? It will increase, isn't it? Because the pressure would be even more. This hasn't changed. The pressure would be even more. So your glomerular filtration rate would increase, right? What happens if you decrease the diameter of the afferent arteriole, leave the efferent unchanged, or maybe even increase the efferent arteriole diameter? So you decrease afferent arteriole diameter. What will happen to the filtration? Pardon? It would decrease, exactly. Do you understand that? So GFR would decrease. And if you think about it, this is what happens logically. You remember we talked of when we were doing aldosterone and so on, we talked of something called renin-angiotensin mechanism, or even ADH. You remember ADH was also called vasopressin, and it caused constriction of blood vessels. So think of it, when your body has lost a lot of fluid, that's when renin is secreted by the afferent arteriole cells. So you don't want to be passing too much urine, isn't it? Because the more filtration occurs, the more urine will be passed. So whenever the body needs to conserve fluid, such as when you've lost a lot of fluid and so on, you'll notice that the afferent arteriole actually constricts because that renin is produced, and renin goes and produces angiotensin, which causes constriction. Also, vasopressin is produced, so that causes constriction. So your filtration decreases, which means urine amount will decrease. So you can see how by changing the diameter of the afferent and efferent arteriole, you change the hydrostatic pressure and you can, increase or decrease filtration. So let's look at glomerular filtration as a review.
Filtration is the first of three main processes in urine formation. Blood flowing from the glomerulus exerts pressure, and this glomerular blood is high enough to push water and dissolved substances out of the glomerulus and into the capsule. This then becomes known as a filter. The wall of the glomerulus contains pores and is similar to a strainer. The diameter of the pores determines which substances flow through and which remain. The only blood constituents that do not move into Bowman's capsule are the larger molecules such as blood cells and most plasma proteins, which exit the efferent arteriole. To summarize filtration, glomerular blood pressure causes filtration through the glomerular capsular membrane to create the glomerular filtrate.
So let's answer a few questions now on filtration. So where does filtrate first appear? Or what does it first enter? So this is your anatomy. So it's a good review of your anatomy. It enters the capsular space. Remember, the filtrate enters the capsular space. When you call it filtrate, what is entering the afferent arteriole is blood. The filtrate is the one which enters the capsular space, okay? Not the afferent. It's blood which is in the afferent arteriole. Remember, filtration occurs through the glomerulus, which is after the afferent arteriole. So it enters the capsular space. So think of this one. This person's filtration membrane was damaged due to, say, severe bacterial infection. So which of the following is not involved? Very good. Yes, the parietal layer doesn't form the filtration membrane. Okay, here you see blood cells and maybe protein in the urine. What do you think has happened? Excellent. The filtration membrane is damaged. Okay, so you filtered this. A lot of important substances got filtered, small molecules, glucose, amino acids, vitamins, all of that. So now you've got to reclaim that. So that second process of urine formation is called reabsorption. So most of it is reclaimed and then it's thrown into the blood. Either you use active process where you use ATP, you might use proteins called transporters, or it may just passively go across like water will passively go across. Reabsorption occurs a movement, and this should read off, it's movement from the tubule into the interstitial fluid, that is the space between the tubule and the blood vessel, and then it goes into the blood vessels. And which blood vessels are these? So it will go into the peritubular capillaries and the vasa recta, because those are the blood vessels which are in close contact with the renal tubule. Some substances to just maintain, remember one of the functions was to maintain blood volume and composition. So maintain the plasma concentration. Some substances are absorbed completely. Like for example, glucose is one of those substances absorbed completely. Some amino acids absorbed completely. Unless it is present in excess. For example, if someone, when we did endocrine system, we talked of diabetes where a person has glucose in the urine. That is because these people have very, very high blood sugar. So as that high blood sugar that blood is getting filtered, the glucose is one substance which is involved in active transport to be reabsorbed. So you have certain proteins which kind of hold on to the glucose and allow it to pass from the tubule into the blood vessels. And those things are known as transporters. Now there are only so many of them. So if all the transporters are saturated, the excess glucose cannot be reabsorbed, which is why you find it in the urine. Okay, so that's why you have what is called glycosuria in diabetes. Water and ions reabsorption, a lot of it occurs in the proximal convoluted tubule, but at the distal convoluted tubule and the collecting duct, this is dependent on the needs of the body and is hormonally regulated. Remember, we talked of water, ADH. If your water levels are low in the body, ADH is secreted. So where ADH acts is here on the distal convoluted tubule and collecting ducts. Same with aldosterone. Remember, it causes sodium reabsorption and potassium secretion. So some amount of sodium will be reabsorbed, but thereafter, by the time the filtrate reaches the distal convoluted tubule and collecting duct, the body's reabsorbed what it wants, then it will look at the filtrate in the distal convoluted tubule and the collecting duct. And remember, in the distal convoluted tubule, you have that macula densa cells which sense the solute content. So then, based on what it is, the body will either reabsorb or remove what is not needed. Okay? So that's why this is hormonally regulated. Even parathormone, remember parathormone causes calcium absorption. Again, if calcium levels are low, that will be done here in the distal convoluted tubule and collecting duct. Let's look a little bit more at reabsorption. The main site of reabsorption is the proximal convoluted tubule. The distal convoluted tubule also reabsorbs substances, but at that point it is hormonally regulated, as I said. The loops of Henle. So you have, if you start from here, this is called the descending limb of the loop of Henle, and this is called the ascending limb of the loop of Henle. So look at this image really carefully. So can you see that in the descending limb of loop of Henle, you can see that water is passing from the tubule, it's passing out. So the descending limb is permeable to water. So water can pass through the lumen into the cells of the distal tubule and then go into the blood vessels. But when you look at the ascending limb of the loop of Henle, look at this, that you cannot see in the ascending limb, in this part up here, water passing through. So here, the ascending limb of the loop of Henle is kind of more or less impermeable to water. So it's impermeable to water, especially the lower regions. In the higher regions, like in this part, in the higher regions up here, in this area, all of this is hormonally regulated. So in the lower regions of the loop or ascending limb of the loop of Henle, only solutes can pass from the tubule into the blood vessel. So only they can be reabsorbed. Water doesn't get reabsorbed. And in the distal convoluted tubule and collecting ducts, here are the hormones. ADH, and this is again a good review for endocrine. You just did endocrine. So ADH is secreted when the fluid volume is low because you want water to be reabsorbed. Aldosterone is secreted when sodium levels become low or potassium becomes very high. Atrial natriuretic peptide, this is secreted, it's an antagonist, remember, to ADH and aldosterone. So this is secreted when fluid volume levels are very, very high. And then parathormone is secreted when blood calcium levels are low so that calcium can be reabsorbed. So let's look at reabsorption. Okay, try it.
Reabsorption is the movement of substances out of the renal tubules into the peritubular capillaries located around the tubules. Water, glucose, chloride, and other nutrients are examples of substances that are reabsorbed during this process. There is a repeated pattern for reabsorption. First, positively charged ions, like sodium, are generally actively transported out of the tubule and into the blood. Then, negatively charged ions, like chloride, follow the large positive charge into the blood due to electrostatic attraction. Then, water follows by osmosis. In the proximal convoluted tubule, the sodium and chloride are transported out of the blood. Then, water follows. In the lumen, the pattern repeats itself. Sodium and chloride are transported out of the tubule into the blood. Then water follows.
And here I want you to pay attention. I'm just going to stop it for a minute. I want you to pay attention. Notice in the ascending limb it only showed solutes passing through, and notice in the descending limb it showed water passing through.
Finally, in the distal convoluted tubule, it's the same thing again, but this time it is regulated by a hormone called AH. Sodium and chloride are once again transported out of the tubule into the blood. Then water follows. In total, approximately 99% of water that leaves the blood by glomerular filtration returns to the blood by reabsorption. This leaves about 1% of filtrate to be excreted as urine. Absorption occurs through active or passive transport. Sodium ions and other ions are only partially reabsorbed from renal tubules. As an example, sodium ions are actively transported back into the blood from the tubules. The amount of sodium reabsorbed varies depending on salt intake. The greater the salt intake, the less the amount of sodium reabsorption. The less the salt intake, the greater the amount of sodium reabsorption, and the less sodium secreted in the urine.
So here you can see how in the distal tubules and collecting ducts, it's hormonally regulated, because as the filtrate passes through, some of reabsorption of water, sodium, all that has to occur, and that occurs in the proximal convoluted tubule. Later, by the time it comes here, that's when the body decides, now do I need to reabsorb more or not? Okay, so as the example was given, if you take too much salt, that means you have too much sodium in the blood, so the body does not want to reabsorb that, so that's when it throws it out. Okay, so then aldosterone at that time would not be secreted. If you were taking too little, then the body sees, oh, I haven't reabsorbed enough in the proximal, now I need to reabsorb some more, and that's when aldosterone will be secreted. Okay, let's answer a few questions on this. What's the purpose of reabsorption? It's to reclaim important substances that get filtered. This is not to provide nutrients for the body, but to reclaim important substances, okay? Because the body took them from the intestine, but now, oops, they got filtered again, so we need to get them back. Which best describes the process of reabsorption? Very good, yes. Substances pass from the renal tubule into the peritubular capillary, and I want to emphasize here again that between the renal tubule and the peritubular capillary, you remember you saw if this was the tubule, or let's say if that was the capillary and I draw the tubule in another color, and here's the renal tubule, right? Remember, it passes from the cell through the interstitial space into the blood vessel. The reason I'm kind of emphasizing this space called interstitial space, because we'll talk about it when we do fluid compartments. So remember that blood vessels are kind of not stuck to the to cells, there's always a space between the blood vessels and cells, and that's known as interstitial space, or also called extracellular fluid space, because it's outside the cell. Okay? The last process is, it's like an oops mechanism. And in one very good example is, like, you know, when you go to a place where they make a waste, what do you call them? A waste, not warehouse, but a place where, you know, all the garbage goes. And imagine you have a conveyor belt, okay? So all the garbage is thrown onto that conveyor belt. And that conveyor belt is, throwing it into that conveyor belt is like filtration. And then as the conveyor belt goes round and round, you know, imagine there are a lot of people who kind of pick out some important things and they remove it. So that's like reabsorption. And then imagine if one of those guys picked out something which was not needed. So it's like an oops mechanism. Oh, what do? I picked this thing which is actually a waste product. I need to throw it back. So they throw it back into the conveyor belt. That is secretion. You understand? It's kind of throwing back. So it's like an oops mechanism or a backup for filtration and reabsorption. Or there may be substances which never got thrown onto the conveyor belt in the first place. So now you didn't start from the beginning, but in the end you can actually throw them back onto the conveyor belt. So can you see that in this secretion, first thing, of course, it is from the capillaries. So this is where the capillaries are going to be. So let me change the color again. So here's where all the peritubular capillaries and vasa recta are going to be, over here. So this is going to be in this direction, right? So it's going to be from the capillaries as shown here. You can see this. It's going from the capillaries through the interstitial space into the tubule lumen. So that's how secretion occurs. The purpose is to remove these unwanted substances so that waste can be disposed of. It could be either they were not filtered at all. So imagine again, so if I show you, here's the afferent arteriole, here's the glomerulus, here's the efferent arteriole, and remember this broke up into peritubular capillaries and the vasa recta. So here, if there were some substances which went this way and went out, so imagine they never got filtered, but now they are lying in the blood. So now you get a way to throw them back. So that's secretion. Or there were substances which were reabsorbed, but we don't need them, and they were only reabsorbed because the concentration was too much, you know, so they went along the concentration gradient. Secretion is also important for maintaining blood pH. Remember, one of the functions of the kidney was to maintain the composition of blood. So imagine if, for example, your blood pH was too high, so it was very alkaline. So what could you do? What you could do was you could reclaim hydrogen ions, you could reabsorb hydrogen ions and throw bicarbonate into the lumen so that it passes out in the urine. So can you see you can adjust the pH? Or imagine your pH was very acidic, so the kidneys can remove hydrogen ions and secrete them into the lumen so that they pass out in the urine. If hydrogen is secreted into the lumen, what happens? Your pH will rise and you can maintain the pH. That's the way the renal system compensates for changes in your acid-base balance. The main site for secretion is the proximal convoluted tubule. So you can see it, proximal convoluted tubule, even for reabsorption and secretion. And if you remember, the cells were much taller in the proximal convoluted tubule. And when we talked of the cells, they also had those microvilli, which increase surface area, which is why most of your reabsorption and secretion occurs in the proximal convoluted tubule. And under hormonal influence, secretion is, potassium is secreted. Remember, aldosterone reabsorbs sodium and secretes potassium. So potassium secretion is under hormonal influence, with aldosterone causing increased potassium secretion, and ANP, atrial natriuretic peptide, causing decreased potassium secretion. Instead, it excretes actually sodium ions. So sodium is pushed out. So here again, you have hormonal influence for secretion too. So let's look at secretion.
Although most of the water and substances enter the tubules because of filtration across the glomerulus, the third process is known as secretion. A small amount of substances from the blood into the tubule. Substances such as potassium, hydrogen, uric acid, ammonium, and drugs such as penicillin and histamine move from the peritubular capillaries into the tubule.
This is the reason why when you people urinary actions, we like to give drugs into the lumen of the tubule. So imagine if someone had urinary infection, the bacteria could be present in the lumen of the tubule or could be present in the cells, right? So you want to give them drugs which could pass from the blood into the lumen, and that's where they're going to act. So often you'll find people who take urinary, any drug which acts on the urinary system, very often the urine gets colored. And it's not because, and the color may be orange or a little bright, and it's not because that they have passing blood in the urine, it's just that the drugs are being secreted. And if they get secreted into the lumen, they can act well on the bacteria over there. So here let's see how the regulation of urine volume and composition, how the kidneys help in it. So the main way they do that is they keep the solute content in your body fluids constant by regulating volume and concentration. So if the solutes are too much in the blood, they'll pass it out. If the solutes are less, they will reabsorb it. If your volume, if the filtered amount is too much, let's say like for example, you drink a lot of water, you don't want your blood volume will go up, so automatically you begin to pass out more urine. So that's how they keep the volume constant. And in this Henle's loop, if you look at this, there are two mechanisms which are present. So can you see this? This is the descending limb of the loop of Henle, and this was the ascending limb. So here, remember, the descending limb is permeable to water, but the ascending limb is not permeable to water. So water goes out from here, but from here solutes go out. So the concentration or the gradient between the cortex and the lower part of the medulla keeps changing based on how much water and how much solutes are being absorbed. And at the same time, look at these vasa recta which travel along. So they also kind of help to maintain this concentration gradient. Okay, so that's how substances are reabsorbed or they are secreted based on this gradient. So let's look at this in a little bit more detail. And this is again a common sense really. When would you produce urine? Suppose you drink large amounts of water. You might have noticed yourself, if you're drinking large amounts of water, where your water or the effect water or your body is well hydrated. The osmoreceptors in the hypothalamus are also well hydrated. So it causes water. So water cannot collecting duct doesn't the body. In the proximal convoluted tubule, the distal tubules and collecting ducts where so here it's the collecting duct and distal convoluted tubules which become impermeable to water. So in the result you produce high volume urine. By quantity, even if you have a little short alcohol by itself decreases urine if they large shots because of produce concentrated urine at a time when your body needs to passing water. This would be anything which causes dehydration. Has been blood loss, hemorrhage, any of those things did. So your osmotic pressure is increased, and so they're able to water. So water is reabsorbed. When more water is reabsorbed, what happens? Your urine becomes more. You have to get dehydrated. You don't the day. By the end of the day, you would notice that you pass less urine and the amount is brighter. Regulated by aldosterone. Remember, the mechanism is dehydration, low blood pressure, or there is less sodium to be activated. Angiotensin, remember, by itself also causes vasoconstriction. So when it weighs urine, will be less. Natriuretic peptide does the exact opposite of aldosterone. What it does is its volume is very high. Say, for example, you've drunk or cardiac failure or any, it will do it wants to get rid of the water out of the body. Sodium is osmotically pulls water or electrolytes is hydrogen and bicarbonate, and this is how pH is regulated. It means pH, that means you have too many hydrogen ions. So hydrogen ions are secreted into the tubules and they pass out in the urine. Your urine high. Then you bring your and instead bicarbonate is secreted. Okay, so you can, all of this is really common at some things. So drank 3 cans of beer. What would be the effect on urine? This will cause dilute urine to be formed, not concentrated. Look at this, you're drinking fluid. The very fact that you're drinking a lot, and think about it yourself. If you drink 3 glasses of water, you tend to just go to the restroom more often. So when you drink fluid, that fluid gets absorbed into your gastrointestinal tract. It will go into your bloodstream. Your blood volume will rise. So that's one. So you don't want that excess blood volume. You pass it out as urine. Second is alcohol by itself, remember I just said, depresses ADH secretion. So with the result, if ADH is not secreted, more urine will be formed and you have dilute urine. Suppose this person is sweating excessively and we assume, since nothing else is given, that they are not drinking water to make up for that sweat. What will this do? Yes, this will cause concentrated urine to be formed. And you would have noticed in summer, we tend to pass a lot less urine than in winter. In winter, we don't sweat as much, so we really visit the restroom more often because the body has to kind of somehow get rid of the waste. But in summer, we tend to sweat a lot, and if you don't kind of replenish those fluids and solutes which are lost in sweating, then you pass very, very little urine, okay? So again, like I said, some of these questions are really just looking at what happens with you in your daily life. So they're really common sense. Let's look at fluid compartments. So water is a major part of your body. It forms 60% of your body weight. And there are basically 2 compartments. And this you must understand. One is the plasma, which is present in blood vessels. The second is remember that interstitial fluid, which I said was between the blood vessel and the cells. And the third is the fluid, the cytoplasm, which is present inside your cells, right? The cytoplasm also is mainly fluid, is mainly water. So based on this, we divide it into first 2 main parts. One is intracellular fluid as the name suggests, this is the fluid present inside the cells. So here when you draw any cells, anywhere, any kind of cell, so it may be cells like in the epithelium, or it may be single cells like red blood cells or white blood cells. All the cytoplasm which is present inside these cells, that is intracellular fluid, and we usually write it as ICF. And this is 2/3 by volume. So you can see over here, it is 40% of your body weight. If your entire body volume is 60%, this is 40%, so it's 2/3 by volume. Extracellular is anything that is outside the cells. It is anything that is outside the cell. This is 1/3 by volume. So here you can see it is 20% of your body weight. So that makes it 1/3 and this makes it 2/3. Extracellular is further divided into two parts. One which is in the blood vessels, because that's outside the cells, right? So that's in the blood vessels, and that is plasma. So that's only 20% of the extracellular fluid. And the second was interstitial fluid, which is 80%. Most of this extracellular fluid is in the interstitial fluid. So again, just with the kidneys, if I gave you an example, so if we draw the Bowman's capsule like this, and we draw the loop of Henle, and go around like this. And I'm just going to use, I should have used a different color, but I'm going to use white for blood vessels. So if you think of blood vessels, let's say the vasa recta, which are present here around, and you remember they had connections with each other. Now the tubule cells, this would be intracellular, right, inside the cell. This area, this space here, which is between the cells of the tubule and the blood vessel, this space is what is called interstitial fluid. It's usually written as IF, interstitial fluid. And this, which is present inside the blood vessel, is also part of this extracellular fluid, and we just call it in the blood vessels. So these two together, the interstitial fluid and the one in the blood vessels, are collectively called extracellular fluid. Okay, so it's really important to understand this concept. So do you have any questions on this before we move on to the next one? So you've understood what is inside the cell, and what is outside the cell can be in two places. It can be in the connective tissue outside the cell, which is called the interstitial space or interstitial fluid, or it could be in the blood vessels, because plasma of the blood vessels. Okay? Got that? Any questions on this? Okay. Let's look at the composition of body fluids. Water, main constituents. It's the solvent. And in water, the solutes which are present are, some are electrolytes, some are non-electrolytes. The main electrolytes are like salts and your acids and bases. Salt, sodium, chloride, potassium, magnesium, zinc, calcium, all of that. The non-electrolytes are like glucose, lipids, urea. So these are what are present. And here's where you've got to recall a little bit of your ANP1, and I'll just kind of refresh your memory. Remember in ANP1 you did the nerve and muscle, and you did something called neuromuscular junction, if you remember, and you thought of something called depolarization. Do you remember that? And even in the nervous system, remember an axon, there was depolarized and there was passage of action potential. You remember that? So just so that you don't have to memorize this, so if you remember this, so imagine a neuromuscular junction. So here is a muscle cell, and here's a neuron which comes and is there. And remember, when the impulse comes, those synaptic vesicles come out and they liberate acetylcholine, which goes and attaches to receptors, and it causes sodium ions to pass into the cell, and then after some time potassium ions from inside the cell go out. You remember this? This was like depolarization and repolarization. Okay, so if we use that, and if you look at it this way, so this is a muscle cell, and this is the inside of the cell, and this is outside the cell. What was present outside? More of sodium, right? What was present inside the cell? More of potassium. Okay, So that's one main electrolyte which is present. So you can see this is outside the cell. That means this is extracellular fluid. So sodium and along with sodium chloride is the main sort of extracellular component. And plasma is part of extracellular fluid compartment. Plasma has a lot of proteins. Remember the plasma proteins, fibrinogen, albumin, gamma globulins, all of prothrombin, all of that, right? So these are main constituents of extracellular fluid. Sodium, and we can add chloride. And if you look at blood vessels, if I draw a blood vessel here, remember in the blood vessels you have the cells. These cells are intracellular fluid. But outside in the plasma, you had a lot of those plasma proteins which were responsible for osmotic pressure. So extracellular fluid, where blood vessels are concerned, they have more proteins. In intracellular fluid, you have a lot of potassium inside the cell. You have a lot of what is called hydrogen phosphate inside the cell. And inside the cells also you have proteins. Remember, if you look at muscle cells, you have actin and myosin. Remember, there were proteins present inside the muscle cell. Okay? So remember in the extracellular fluid, you have sodium and chloride, and you have a lot of in the plasma, a lot of proteins. In the intracellular fluid, you have potassium and hydrogen phosphate and also some proteins. If we look at this in a chart, and you take a chart up here, so the red shows blood plasma, the blue shows interstitial fluid, the two together, so actually it's the two together. The blood plasma and interstitial fluid, both together are extracellular fluid, and intracellular fluid is the one inside the cells. So let us look at some of the substances. So let's look at sodium. So remember, sodium was more outside the cell. So see this, sodium, a lot of it present in the interstitial fluid, a lot of it present in the blood plasma, very little present inside the cell. The next one was chloride. Remember, chloride too, a lot of it was present outside the cell, less inside. So look at this chloride. A lot of it in interstitial fluid, a lot of it in plasma, both outside the cell, less present inside the cell. Let's look at potassium and hydrogen phosphate. So when we look at potassium, see this, more inside the cell, less in the plasma and interstitial fluid. And hydrogen phosphate, again, look at it, a lot of it inside the cell, and you'll see this in the kidney tubule, how it becomes important. Very little outside the cell. And then let's look at proteins. So if you look at proteins up here, see, notice how in the plasma you have a lot of proteins, plus inside the cell you have a lot of proteins, okay? I don't expect you to remember all of these others, but I would like you to remember, because you did it in ANP1, where sodium, where potassium ions are more, where chloride and phosphate are more, and where proteins are more, okay? Okay, let's stop here because this concept is going to take a while, so we'll do this next time.